In this video, I just wanted to touch upon a couple areas of caution to think about when you're doing linear regression, specifically extrapolation or extrapolating, and then lurking variables. So when we talk about extrapolation, what we're talking about is what happens when we're making predictions. So when you're making predictions, remember you're plugging in a value for x. So if I'm making a prediction with an x value that's outside the data range. So for example, with this data, my x values go from 6 to 20. So making a prediction with any x value between 6 and 20 inclusive, so that means including 6 and 20, is an acceptable prediction. So we can only make predictions within the x values that are contained in our data. If we make a prediction with any value less than 6 or greater than 20, then we will call that extrapolation. And this is dangerous because it assumes the model continues outside of the range that we have in our data, and we can look at in our scatter plot and then where our least square regression line was calculated. So a lot of times you'll see this in a question where they'll ask you to do a prediction. So they might ask you, like for example, in this question, they might ask you to make a prediction where the volume is 30. And then after you do that, the next part of the question might say, how confident are you in this prediction? And what they're looking for you to say is you are not confident in this prediction because it's an extrapolated value. It's outside the range of values from the data set, and therefore it's dangerous to assume the model continues. The second thing that we want to consider an area of caution is what we refer to as lurking variables. So this is a variable that's causing both your explanatory and your response variables, so both your x variables and your y variables, to change. And it cannot be removed from the model. So it's some variable that we cannot block for, or we can't account for in any other way. So let's say we have a model and it shows a strong positive linear relationship between elementary students' weight and the measure of their reading ability. So do we want to try to make elementary students weigh more so that we can get a better reading ability? So what we need to think about here is that there's possibility of a lurking variable, and in this situation my lurking variable is age. And so the age is really the variable that is affecting both of those things. As an elementary student gets older, they tend to get heavier, they're going to weigh more because they're growing, and hopefully they're also having their reading ability increase as well. So age is affecting both the explanatory and the response variable, but we can't separate it from the other factors. We can't remove it in any way. Okay, so here we have a data set where we have the computer output, and we're using that computer output to describe a car's cost in terms of its age. So finding the least square regression line, remember we're just going to take these coefficients or these estimates, and we come up with our least square regression line. So the cost of the car is $12,319.6 minus 924 times age. We want to find the correlation value. So remember here we're going to take the r squared value. We have to take its square root, and then we have to look at the slope. So this is my slope here. My slope is negative, so my correlation is going to be negative. So remember, my slope and my correlation always have the same sign. So if all we have is r squared, we're going to take their square root, but then we need to check the slope to find out what sign to put on that. We're going to make a prediction for the car at age 6. So my prediction is found by plugging in 6 for the x value, and we get about $6,775.60. The residual here is going to be the actual value, so I'm going to get the actual value from the actual table of values. So this 5,990 is my actual value minus my predicted value, which comes from my equation. So we end up with a negative $785.60. In D, they asked us to predict the price and calculate the residual again for a car of age 20. So I plugged in the 20 to get my prediction, which is negative $6,160.40. And then we cannot calculate the residual here because we do not have 20 in our table. So there is no way for us to calculate the residual in this particular case. Also notice that the prediction is a little bit absurd because we can't have the value of a car being negative amount of money. So this is a situation where what we're talking about here is this prediction that we did here in D was an extrapolation. It was outside of our data model. for the X value, and that is dangerous because it assumes that our model continues. And so we're making some assumptions there about the data. So in this situation, actually, a car the value decreases as it gets older, but after a certain point, if you keep a car in good shape and you keep it long enough, then it becomes an antique and its value would begin to increase again. So we can't assume that the model continues forever. Okay, this example, it says there's a strong positive association between the amount or strength of anesthetic used in surgeries and the death rate as shown below. So we can see the scatter plot there, and we can see that we have a pretty decent model, probably a moderate relationship, but it does appear to be linear. So does this suggest that we should ask for less anesthetic in our surgery? So what we're thinking about here is that there's a lurking variable, and that lurking variable is the severity, length, or complexity of the surgery. The more complex and longer the surgery, the more anesthetic that's needed, and then the higher the death rate's going to be. So we want to always kind of think about our situation, and is there a possibility for a lurking variable? In a second example here, there's a strong positive association between the number of firefighters at a fire and the amount of damage. So what could be a lurking variable? So again, if you're having a fire, do you want to just ask for fewer firefighters because there's going to be less damage? No, because there's a lurking variable here, which is the intensity of the fire. The more intense the fire, the more damage that's going to be done, and the higher the number of firefighters that would be deployed to your fire.